Good morning. Yes, this was the Gödel fanfare. Some of you already heard it. We used it for the Vienna Summer of Logic keynote lectures, and it was composed like the string quartet that we had at the award ceremony on the occasion of this event. The most exciting moments in the history of science are paradigm shifts. And I think it is fully justified to say that model checking is such a paradigm. Is such a paradigm shift? Whatever. Is such a paradigm shift. And today we have Ed Clarke as our keynote speaker, who is one of the big driving forces behind model checking. Right? He received numerous awards. Let me just mention the Turing Award. Let me mention the more recent Bauer Award of the Franklin Institute, which, as Ed says, is an award for science, real science. And I think model checking did much, not just for verification, but it did a lot for the credibility of logic in computer science at large. And model checking also has been a catalyst for the use of theorem provers, for instance. Let me also add that Ed not only was there for the invention of model checking, but for all these smaller paradigm shifts inside model checking which really drove the field. Symbolic model checking, you saw Ed. SAT-based model checking, Ed again. Abstraction refinement, guess who? So I'm asking Ed now to give his keynote address.
Can everyone hear me? I want to thank you for tracking down the location of this lecture, my lecture this morning. I was quite surprised to find that it wasn't in the building where we had been listening to lectures all week. Let's see, I turned 70 next summer, and I have decided to follow Dana's example. I remember that Dana retired from CMU when he turned 70, so my current plan is to retire next year. It doesn't mean that I'm going to stop doing research, but it does mean that I'm going to stop teaching undergraduates. But this talk is something of a retrospective on model checking. It talks about what model checking is and some of the difficulties and how we overcame them. And then at the end, I'm going to talk about some new work that I'm quite excited about, how you can model check reactive systems that involve both discrete and continuous behaviors. So the basic idea behind model checking is extremely simple. The specification language is a propositional temporal logic. Temporal logic is a notation for reasoning about the ordering of events in time without introducing time explicitly. You can say that one event must precede another, or that two events don't happen at the same time. It was originally developed by philosophers and linguists for reasoning about the use of tense in natural language. And it was Amir Pinwelli, I think, who proposed to use it for specifying computer programs. The verification procedure is an exhaustive search of the state space of the concurrent system to determine the truth of the specification. And originally, it was developed for finite state concurrent systems. We observed that a number of synchronization skeletons were finite state, and we could reason about them in this manner. Model checking has a number of advantages. You don't have to construct a proof. It's algorithmic in nature. It doesn't require that you spend an enormous amount of time constructing the proof of correctness. It's quite fast when it's applicable. It's not always applicable. If the specification is not satisfied, the model checker will produce a counterexample that shows why the specification is not satisfied. There's no problem with partial specifications. You don't have to completely specify the system to get information about its correctness. And the logics can easily express many properties of concurrent systems. Now, of these, probably the most important is the counterexample feature. A model checker can often produce a counterexample that will take you directly to the source of an error in a program or protocol or circuit. Now, the main disadvantage is the state explosion problem. The state explosion problem can occur if there are too many processes, or in digital hardware terms, if you need too many latches. And much progress has been made recently. I think that that's actually true. We've made continued progress on this problem over the years. And the recent progress that we've made has been to be able to verify reactive systems that involve continuous and discrete behaviors. Now, the models that we reason about are label state transition graphs, are crypt key models like the one at the top of the slide. Each state is labeled with a set of atomic propositions that are supposed to be true in that state. So A and B are true in the red state, and C is true in the green state. And if a proposition doesn't label a state, we use the convention that it's false in that state. So C is false in the red state, and A and B are false in the green state. If we fix one state as an initial state, then we can unwind the label state transition graph into an infinite computation tree. Now, we don't actually do this unwinding, but we use the unwindings to give the semantics for the operators of our logic. The logics that we use, we call computation tree logics. They are constructed from path quantifiers, which quantify over paths that start at a given state, and temporal operators, which describe the behavior along a particular path. So some examples are shown on this slide. Let's see. The last line didn't quite make it, but I think you can guess what the symbols, missing symbols were. We assume that the root of each computation tree is S0. The operator AG, little g, holds at the root of the first computation tree because along every path, G holds globally. Holds at every state. So G holds at every reachable state. AFG holds at the root of the second computation tree because along every path we eventually reach a state where G holds, or sometime in the future we get to a state where G holds. In the first computation tree on the second line, EFG holds because there exists a path, and at some point in the future along that path, G holds. We say that G can possibly hold. And EG little g holds at the root of the last computation tree because there exists a path, that's the E, and G holds globally along that path. We say that G is potentially invariant. Now, here are some properties expressed in CTL. EF started and not ready will be true if there exists a path, that's the E, and at some point in the future on that path, there's a state labeled with started and not ready. The formula will be true if it's possible to get to a state where started holds, but ready doesn't hold. So this might represent some anomalous condition that we want to check for in a circuit or a protocol. AG request implies AF acknowledge. Specifications with this format occur quite frequently. Globally, if a request is issued, then inevitably in the future an acknowledgement will be received. AF device enabled will be true if no matter how far we go out on a computation path, it's inevitable that device enabled will hold. And this means that device enabled holds infinitely often on every computation path. Now, AG EF restart will be true if no matter how far we get out on a computation path, it's always possible to get back to the restart state. So the system can't be deadlocked. You can't get it into a state from which it's impossible to get to the deadlocked state, get back to restart. Now, the model checking problem is very easy to state. Let M be a state transition graph obtained from a concurrent system, and let F be a specification expressed in temporal logic. We want to find all of the states S of M where the formula F is true, and we want to check if the initial states are among these states. Now, Alan Emerson, Prasad Sisla, and I gave efficient algorithms for this problem way back in the mid-80s, even though the basic CTL model checking algorithm was linear in the size of the formula and in the size of the formula and in the size of, in the linear in the product of the size of the formula and the size of the state transition system, it was of limited usefulness in practice because of the state explosion phenomenon. You couldn't even get computers that could hold the state spaces in order to be able to search them. So this is the structure of our first model checker, the EMC system that I built at CMU, and the state transition system would take a state transition graph with maybe 10 to the 4th or 10 to the 5th states and a CTL formula and would produce either true or generate a counterexample. Again, that information was very important. Now, symbolic model checking is the method that's used by most industrial strength model checkers. It uses a Boolean encoding for the state machine and sets of states, and it can handle much larger designs, hundreds of state variables. And BDDs are still frequently used to represent Boolean functions. It was a very good idea. Now, Ken McMillan was not the only one who had the idea of using binary decision diagrams. By the way, Ken, I don't know if he's still here, but he had the idea for binary decision diagrams really in the first month that he was at CMU as a graduate student. So it was amazing. Let's see. BDDs enable us to handle larger systems, maybe an order of magnitude increase in the number of hardware latches. And we wrote a number of we wrote a number of papers seeing how many states we could verify using symbolic model checking, and we pushed the count up to 10 to the 20th power very quickly, and then 10 to the 40th power and 10 to the 50th power, even all the way up to 10 to the 100th power. And then we decided that maybe number of states alone wasn't a good measure of the complexity of a system. But I've never found a better measure of the complexity of a system, maybe log of the number of states. Now, the model checking algorithms that we use, especially in the BDD-based case, are fixed point algorithms. The EFP, which means possibly P, will be true at a state if P holds at that state, or the state has a successor, and the state has a successor, and EFP holds at that state. And in fact, we can show that EFP is the least such fixed point of the function P or EX. Well, it's the least fixed point of this expression. And if another set satisfies the same fixed point expression, then the set of states that satisfy EFP will be a subset of U. And for that reason, we write that EFP is the least fixed point with respect to U of P or EX U. This means that we can use the induction technique that Dana described made and wrote about in many papers. We start with false of the empty set. We compute U1 as P or EX U0, U2 as P or EX U1, and so on. And if two sets of states are the same, then, if two states turn out to be the same, two sets of states turn out to be the same, then nothing will, the set of states will reach stability. So if let's suppose that U1 was equal to U2, well then U1 here would be equal to U2, so we would have that U2 is equal to U3, and so on. Now, we are guaranteed a test for convergence if we represent the sets of states using binary decision diagrams, because BDDs are a canonical form for Boolean functions. If we write these as, if we express these sets of states using Boolean functions and represent them as BDDs, then we really just have to test and see if two pointers point to the same data structure to determine whether we have convergence or not. So this is very quick. Now, to see how this would work in practice, it's easy to see. Let's suppose that we have this four-state state transition graph, and we want to determine whether P is reachable from S naught. We start with false, or the empty set of states. We compute U1. A state will hold at a state will satisfy U1 if it either satisfies P or if it has a successor that satisfies U0. And so we get this approximation. Then we compute U2. A state will satisfy U2 if it either satisfies P directly or has a successor that satisfies U2. And then we compute U3 next. A state will satisfy U3 if it either satisfies U2, P directly, so we get this state, or if it satisfies U2, in which case we get this approximation. So we actually get convergence after 2 steps. If we repeat the process, we get exactly the same red states. We can represent the tree using ordered binary decision trees and diagrams. A binary decision tree is, I think probably all of you know what ordered binary decision trees are. If you have a Boolean function, then you can represent it. Suppose it depends on A1, B1, A2, and B2. Then an assignment will satisfy the Boolean function if it corresponds to a path from the root to a leaf. So 0, 0, 0, 0 will satisfy the formula. 0, 1, 0, 1 will satisfy the formula as well. Wait a second. What did I say? Nonsense. Yes, that was true. But 0, 1, 0, 0 wouldn't satisfy the formula, so it leads to a terminal node of 0. 0, 0, 1, 0 would. 1, 1, 1 would. Now, an ordered binary decision diagram is an ordered decision tree where all isomorphic subtrees are combined and all nodes with isomorphic children are eliminated. For a given parameter ordering, the ordered binary decision diagram is unique up to isomorphism, and that was the property I was using a few minutes ago in the example. Randy Bryant came up with the idea for this data structure, and it was the case that for many years, if you went to an IEEE transaction, if you went to an IEEE meeting on computer-aided design, the papers they would contain clever representations similar to Bryant's for representing Boolean functions. Now, for the comparator example, if we use a different variable ordering, then we obtain this BDD. Or if we use the variable ordering in which we interleave the A variables and the B variables, we get this binary decision diagram. And if we, this is very sensitive today, if we put the A variables before the B variables and construct an ordered binary decision graph, then we get a different structure, and it looks like it's somewhat bigger. And if we, you can prove that if we use the interleaved ordering, the number of vertices will be increase linearly, and n. If you put all the a variables before all of the b variables, the number of vertices will be exponential will grow exponentially in n. And moreover, there are some Boolean functions that have exponential size OBDDs for any variable ordering. And you might think that they would be very difficult to construct, but it turns out that they're very easy to construct. An example is the middle output bit of a combinational circuit to multiply two n-bit numbers. Now, logical operations can be performed on BDDs very easily. We can find the negation of a BDD, of a Boolean formula expressed as a BDD just by changing the, replacing each leaf by its negation. The logical conjunction of two BDDs is found by using the Shannon expansion. And here, I hate to do this, but I switch to the Boolean algebra notation, I guess, for Boolean functions, the notation that electrical engineers tend to use. F and G will hold if it's either the case that A is false and F restricted to A bar and G restricted to A bar will be true, and or A is true and F restricted to A and G restricted to A holds. So we're able to break the problem into two subproblems, and we solve each of the subproblems recursively. We always combine isomorphic subtrees and eliminate redundant nodes, and we put we build these structures in a hash table. So all we have to keep track of is a pointer to the graph structure for the BDD. The number of subproblems is bounded by the length of F times the length of G. Now, disjunction, you can also easily find find out what there exists A, F is. You just take the disjunction of F restricted to not A and F restricted to A, and F restricted to A bar is obtained by replacing all A nodes by their left subtrees, and F restricted to A is obtained by replacing all A nodes by their right subtrees. So this is easy to do too. Of course, you have to minimize, you have to traverse the data structure and again make sure that it's that it is in minimized form. Now, how do we represent state transition graphs with ordered binary decision diagrams? Well, we assume that the system behavior is determined by n Boolean state variables, v1 through vn. The state transition variable, the state transition relation will be given as a Boolean formula in terms of two copies of the state variables, v1 through vn for the current state and v1 prime through vn prime for the next state. We now convert t to an OBDD. Now, here's an example of how one might represent a state machine with a Boolean function. you assume that there are two states, and one is labeled with A and not B, and one is labeled with A and B. And we would construct, we would have the conjunct, the disjunct rather, A and not B for this state, and A and B for this state, for this edge. And we would have A and B, and A primed and B primed for this edge. And finally, we would have A and B and A primed and not B primed for this edge. And now we take this formula in disjunctive normal form and represent it as an OBDD. Now, that's not as easy as it sounds, but we don't build up. What we have to do is build the ordered binary decision diagram as we go along. We don't just we certainly don't want to build this first and then convert it to an OBDD. That would be terrible. That would be very complicated. So let's suppose that we want to determine whether EXP is true. We want to find the states where that formula is true. Now, EXP will be true at a state if there exists a successor state and that successor state satisfies P. Well, if we introduce variables for the if we introduce the state variables, in fact, we need 2 copies of them again, and we use an existential quantifier for the path quantifier here, then this expression will represent the set of states where P holds. The set of states V that satisfy this formula will be those where EXP holds. Now, it's a little bit more complicated for formulas involving the fixed point operators. EFP is a least fixed point with respect to U of P or EXU. Look at this part, the part following the dot. We introduce state variables again, and we replace the next time operator by an existential quantifier. And now, let's see, a state will satisfy this expression if P holds at the state, or it has a successor where U holds. A state will satisfy this expression if P holds at the state, or there is an assignment V bar prime that's a successor of V that satisfies U. And now we can compute the sequence of assignments that satisfy this formula, and we can determine when we have convergence because BDDs are a canonical form of Boolean functions again. Now, symbolic model checking with BDDs is probably still the most widely used technique for model checking, but there are alternatives which are better. There are some problems with BDDs. They often become too large. The variable ordering must be uniform along all paths in the tree that you construct, in the decision tree. Selecting the right variable ordering is very important for obtaining small BDDs, and that's often time-consuming or needs manual intervention. And sometimes no space-efficient variable ordering exists. So we came up with a technique called bounded model checking. that is an alternative to symbolic model checking that uses SAT procedures. Now, SAT procedures operate on Boolean functions, but don't use canonical forms. They don't suffer from the potential space explosion of BDDs, and they use different orderings, different split orderings on different branches, and very efficient implementations are available. I believe that Graham Sokolow is in the audience, and he can certainly attest to that. Now, bounded model checking uses SAT. We can, instead of BDDs, we construct a Boolean formula that's satisfiable if and only if there is a counterexample of length k. And then we look for longer and longer counterexamples by increasing the bound k. Now, after we have incremented the k sufficiently, we may decide that there's no no assignment exists, and we may wonder if we can stop. And it turns out, for example, that for safety properties, the number of iterations that you need to check is bounded by the diameter of the finite state machine. And bounded model checking finds counterexamples fast. This is due to the depth-first nature of SAT search procedures. And it finds counterexamples of minimal length as well. And that helps with understanding the models that we construct. And it uses much less space than BDD-based approaches. It doesn't need manually selected variable ordering or costly reordering. You can use the default splitting heuristics that come with most SAT solvers are sufficient. And bounded model checking of LTL formulas doesn't require a tableau or automaton construction. Now, we implemented our first bounded model checker in 1999 when Armin Beer was visiting, and it accepts as a subset of the SMV language. The BMC outputs a formula that's satisfiable if and only if there exists a counterexample of length k. If a counterexample exists, then you can just take the SAT formula and relatively easily find a truth assignment for the formula. Now, Armin gave me a very good example of a very good example of a circuit that had 10,000 latches and 10,000 inputs, and bounded model checking required a Boolean formula that had 4 million variables and 12 million clauses in conjunctive normal form. And the shortest bug of length 37 was found in 69 seconds. So this has significantly increased the power of model checking techniques. Now, it uses LTL rather than CTL. It uses in LTL. We just have the we have the LTL operators X, G, F, and U, and the formulas that we check have a single existential path quantifier, And finding a witness for EF is equivalent to finding a counterexample for A not F. You can use this to take a property that is universal and convert it to an existential that you can check. Now, let's see, where did the system is described as a Kripke structure, again, where S is a finite set of states and I is a initial, I is a predicate in this case that describes the initial states, a Boolean function that is true for each initial state. The transition relation relates pairs of states when it tells you when state S has successor T, and we need a labeling function that labels each state with a set of atomic propositions true in that state. But the data structures are relatively simple. Now, here's one of my favorite examples. It's in the book that Orna, Duran, and I wrote. It's a microwave oven controller, and if you follow the paths in the microwave oven, you can see what that it makes at least that it's a plausible microwave oven controller. Tilde means not, so in the first state, start, close, heat, and error are all false. You can close the door, you can press the start button, then the oven will begin to heat up, and so on. Now, the crucial number here is the diameter of the label state transition graph, which is the least number to reach all reachable states. In other words, if a property holds for k greater than or equal to the diameter d, the property holds for all reachable states. It turns out that finding the diameter can be computationally hard, however. Finding and this is one of the paradoxes of this type of representation. We all know that finding the diameter of a graph is really easy. You use the Voigt-Warshall algorithm, and it's quite simple. But in this case, we have to use a formula, a QBF formula, in which we say that there exists a sequence of states S0 through Sj such that S is equal to Sj, the argument of R is equal to Sj, and I holds at the start state, and there's a path that follows these states that takes us through the transition relation. And if k is greater than or equal to the k will be greater than or equal to the diameter d if for all s, if S satisfies Rk plus 1, in other words, if S makes this formula true for k plus 1, then it will make it true for all j less than or equal to k as well. But checking this requires an efficient QBF checker. This has an alternation of quantifiers, and that's what causes the difficulty in QBF solving. But in some cases, it's still possible to do relatively efficiently. Okay, this brings me up to the recent work that we've been doing, and let's see, have I used up all of my time? What time did I start? About 10 minutes of?
Oh, yeah, just 1 minute.
Pardon?
There's 15 more minutes.
Okay, good. So I'll go through some of this and maybe at least you will see what the problem is. So the systems that you really want to reason about are not always as simple as the microwave oven controller. Sometimes you want to reason about what are called cyber-physical systems. I suspect the name was due to Pinwelly. The typical systems are hybrid automata, and hybrid automata are due to Allure and Hensinger and are widely used for modeling cyber-physical systems. They combine finite automata with continuous dynamical systems. They pose a grand challenge for formal verification because reachability for even simple systems is undecidable, and existing tools tend not to scale on realistic systems. So let's look at what a hybrid system might consist of. There is a continuous state space, and there are a finite number of modes, or states. And init will correspond to a subset of modes and assignments to the continuous state variables. The flow of the system is given by an ordinary differential equation that tells us what the flow is when we're in a given state x at time t. Now, there can also be discrete jumps. The system can be switched from mode q, state x, to mode q prime, state x prime, by resetting the modes and variables. Now, here is an example that occurred in a research project that we were doing just recently. It's a cardiac cell model. It models and you can tell that it's a highly, it's a very complicated ODE system, and it would be hopeless to try to solve this with standard, to get a symbolic solution of this ODE. But of course you could get a numerical solution of the ODE system fairly easily. The solution curve alpha of t is given by alpha naught plus the integral of the flow from 0 to t, and we can define a predicate. In the case we just have a single differential equation, the flow would be from alpha 0 to alpha t, and in general, if we have multiple, almost finished, if we have multiple unsafe states, and we can describe the initial transition by this formula. It starts in x naught. There's an initial transition from x naught to x, and x is unsafe. Let's see, I guess we're describing it recursively, and this is if it had just one transition. And again, here's the reachability formula in case there's just one jump, and if x is reachable in k plus 1 discrete jumps, then it will be reachable in k plus 1 jumps. If it's reachable in k jumps, there's a transition from xk to x prime k, and then the flow takes us from xk prime to x. And we can describe what it means for a system to be unsafe with n discrete jumps by this formula, where unsafe is, again, true of a state if if its argument doesn't correspond to a safe state. Now, we've shown how first-order formulas over the reals can encode formal verification problems for hybrid automata. So this formula is a first-order formula over the reals. Now, we need to be able to decide the truth value of formulas which include nonlinear real functions, polynomials, exponentiation, trigonometric functions, solutions of ODEs, which mostly which have no closed form, and they have high complexity. Even if you just have if you augment polynomials by sine and cosine, it's undecidable to whether a formula is satisfiable or not. Now, what we have done is to develop a new technique called, let me see if I can skip a little of this. Let me see. All I really need to show you is, yeah, I can skip to here, I think, without losing the flow, and I can save some time as well. What we want to know is whether about the satisfiability of a quantifier-free formula under numerical perturbations. So if we have a formula in disjunctive normal form like this, where we've introduced slack variables to convert the individual inequalities into equalities, then a delta perturbation will be a formula of this form, where C has magnitude less than delta. And we've developed a decision procedure that uses numerical techniques, and we build in an error, delta, that guarantees that if phi is decided as unsatisfiable, then it is indeed unsatisfiable. And if phi is decided as delta unsatisfiable, then under some delta perturbation C, phi perturbed by C is satisfiable. So let me show you an example. I think I've got a diagram here that explains this better. Let me skip that. Here, if this formula, which says that the state x is reachable and that x is unsafe, if that is unsatisfiable, then certainly the set of states is safe. If the set of if we can definitely reach a bad state, then we classify this case as unsafe as well. If we are very close, if we come within delta of a bad state, where we fix delta beforehand, then we will automatically classify this as delta unsafe because it's too close to call to make a decision. And we've built my student Zhixian Gao, who has been here this week. I don't know if he's in the audience. He has built a tool that implements this procedure and has used it on all sorts of different examples. There's an elaborate website with examples and the code, the source code included if you want to modify it. And it can provide proofs of correctness if you want them. The tool is really a tight integration of interval arithmetic, constraint solving, and numerical integration. So it just so happens that the code that they developed also is useful on the Kepler conjecture. Some of you may have heard about this problem. It has to do with packing of spheres with cannonballs, and it was proposed by Kepler. There is a professor at the University of Pittsburgh who has been working on this problem. He has a numerical proof, but when he went to publish his result, the reception of the referees of the journal was that it looked right, but he really needed to validate the real inequalities in some way, and we have been using the tools developed by Zhixian Gao for this purpose, and D-Real solves about 95% of the formulas very, very quickly. Now, the cardiac cell example, again, no other symbolic model checker can handle this example, but the tool that Zhixian Gao, D-Real, is able to analyze it, and it can check for various properties like ventricular tachycardia, which is a very serious problem. We can study by using different types of queries. We can study the behavior of the system very close to where it would begin to some form of fibrillation would begin to set in. And there we have 200 highly nonlinear ODEs and more than 600 variables. And the counterexamples that were found by D-Real were confirmed by experimental data, which is good. And you can get counterexamples using D-Real also. Now, this brings me to the end of my talk. Turing was interested in understanding numerical computation, and we have gotten to the point in our work where we're beginning to study again numerical computation. And we use computability over the reals in formal verification of such systems, and we have a practical solver, DReal, which is located on the web, and it is, we are, in addition to the Kepler conjecture, we've used it for finding parameters for in cancer treatment models and for verifying autonomous vehicles. So we're happy with this direction of our research. So I think that's the end of my talk, if there are questions. Or if it's still time for questions. First question for Moshe, always.
So about 20 years ago, you wrote about world-level model checking.
Let's put this back up again. Yes?
So 20 years ago, you wrote about world-level model checking.
Yes.
But at the time, we did not have good SMT solvers. Now today, we have good SMT solvers. But for some reason, I don't think we see around us really good world-level model checkers. Could you comment on that?
Well, let's see. This does, in some sense, what I described at the end of my talk, does in some sense allow you to do word-level model checking. You can talk, for example, about reals. We are also, though, trying to develop a tool now that, let's see, the reals that I mentioned in this last part of my talk are, they are, the honest to God, real numbers. But you'd also like to be able to check floating point numbers with all of their idiosyncrasies. And it seems as though we will be able to do that as well. And I think that was what we meant by word-level model checking all those many years ago.
Right, but you're at the time thinking about hardware. And still, I agree, this is word level. But I don't quite, I'm kind of puzzled why in the hardware area we don't see that the standard is word-level model checking. People still do bit blasting.
Well, let's see, I'm not sure in what sense I used the term word-level model checking all those many years ago as well. There are types of model checking, parameterized model checking, for example, that may be able to address those issues. But I'll have to look back in some of my old slides and see if I can find out what I meant by that term. But this direction I think is a good one to pursue right now.
So in the case of microwave oven or some hardware system, you know the complete state transitions. And when you talk about biological system, there are some things that you know about it, but there are some other part that you're not sure about. And if you want to apply model checking techniques to those problems, how can you address?
Well, let's see. That is a challenge. We've got examples of biological systems where there is where we would like to be able to reason about them using model checking techniques. And what we have to do is somehow come to grips with the chemical formulas, and that's not easy. I was very interested in biological systems for several years, but have now stopped working on them.
Do any probabilistic considerations enter into your own work?
Well, not into my own work, but there is some very good work on that by Marta Kwiatkowska at Oxford, and we could do that. In fact, we've built some special purpose probabilistic model checkers, but and I think that would be very useful direction to pursue. But I haven't made it the main thrust of my work yet.
Did you think about combining your D-real system with systems like Mathematica or other tools which allow you to solve differential equations, even partial differential equations?
Let's see. First of all, partial differential equations would certainly require more intensive study. I know a little bit about those that I learned as an undergraduate, but I would need to really think hard about that. As far as combining this with Mathematica, it might be possible to do that, but we have been looking at examples where we don't have to do that recently, or where that doesn't give any added benefit. Because usually the average differential equation is not solvable in closed form. It's a mess, and you want to have a numerical solution. So we've been trying to use numerical techniques.
Okay, thank you again. Wait a moment. Can you wait? We have a few more things. We wanted to take the opportunity, since this is the last plenary meeting of the Vienna Summer of Logic, essentially to thank a couple of people who played a very important role in doing this. And so, can you please wait a few more moments? So we are almost, the Vienna Summer of Logic is almost coming to its end, and yeah, it was quite a big event. If you count the conferences like to the traditional scheme, it is 13 conferences. They just joined together to form the 8 Flock conference, 74 workshops, 14 competitions, an unbelievable number of 1,269 talks. I'm sure it's an approximation, with a large number at the workshops organized by Stefan. And this was complex. Yeah, and I think Stefan knows more about this picture, right? And indeed, that this doesn't turn into chaos. We have to thank a lot of people who did tremendous work. Yeah? A few people have the visibility because they stand on the stage, but indeed it is all the other people.
It's also possible to model check mechanical systems.
Yes, we will try to do this. In fact, what we did run here was a fault-tolerant distributed algorithm, and they are not so easy to model check.
I can model check the previous system.
Yes. No, because you really had to rely on a lot of people, trust a lot of people. Nobody at these conferences all the information in an individual head. Right? It's all really assume guarantee reasoning, if you like. Okay, so many people to thank. Yeah. Yeah, and we can just, can everybody from the organizing committee who is here stand up? Katharina is there, Thomas Bani is behind the web page, Tony is behind a lot of the technology. Is Matthias here? Yeah, so let's just thank all these people together who in the... who in the background did incredible work and showed incredible enthusiasm. Yeah, and we are really indebted to everyone of you. Of course, then there also is our friend Moshe Vardi, and there is Roderick. And Moshe, of course, is, if you see the Vienna Summer of Logic as an extension of Flock, then Moshe, of course, really is also the founding father of what you see here. And Roderick is a special...
Present. So the PC chairs of all the Flock conferences have gotten together to say thank you. We have already said thank you to the VSL organizers at Schönbrunn, but Moshe wasn't there. So this will be our opportunity. Can you come up, Moshe? We have a little present for you. So maybe if there's any PC chairs of Flock conferences here, maybe you can stand up and this is your present. So this is it, a small token of appreciation. It had to be small because you're in the plane. So thank you, Moshe.
We missed an opportunity to do a great video for this event, and it would have shown me...
You're still on video?
It would show me running around like this, singing about the sound of logic.
You're on video, go ahead.
Not without rehearsing.
Okay, no, it really has been a very good experience to work with Moshe. It has been very smooth, very, yeah, thanks a lot.
So, all I really did is got other people to do the work, and they're really a small number of people that we have in a project like this. We probably have dozens and many dozens of people involved to if an event like this. But Matthias Baz, is Matthias here? Matthias Baz has been really the organizing of the whole Vienna Summer of Logic, which is probably the biggest event in logic in the history of at least this part of the multiverse. And Helmut has been the local spirit behind Flock, which is, I think, also the biggest Flock that we had ever. So really, and then we had Vesna, who may be here, and Katharina, who may be here, and they all deserve a huge applause. But it's not over yet. Go back to hear more talk.
Yes, after I said 10:40, the taxis are going there.
From where?
Let me also mention that the coffee break here is for a relatively small conference, so it may be wise to use the coffee breaks also in the building of Flock.